In this video, we are going to go through the calculations that are a part of chapter 17 in our book, which is additional aspects of aqueous equilibria. The first part of the chapter kind of still focuses on some acid-base equilibrium problems that similar to what we were looking at in the last chapter. And then our focus switches over to the solubility product constant, and we'll look at some problems that are involving those calculations. So what we're going to look at first, the problem that we have here is we're still looking at pH. So we say, what is the pH of a solution made by adding 0.30 moles of acetic acid and 0.30 moles of sodium acetate to enough water to make 1.0 liter of solution? So in this problem, we have an acid, and then we have sodium acetate, which is a salt solution. And what we're looking at here is the pH when a common ion is involved. If we look at the formula for acetic acid and the formula for sodium acetate, we see that they have the acetate ion in common with one another. So we have a common ion effect here, which is the acetate ion. In any problem that begins like this, where we're asked to find the pH of a solution by mixing different solutes together, we have to follow a series of steps. So the first thing that we have to do is look at the solutes in this problem and determine which ones are the strong electrolytes, what are the weak electrolytes, and what is our major species that are going to be a part of the solution. So in looking at that first step, we know that acetic acid, CH3COOH, is a weak electrolyte. And then sodium acetate is a strong electrolyte. Remember, the strength of our electrolytes has to do with how completely they dissociate when we put them into a solution of water. So the major species then are going to be our acetic acid, CH3COOH, which is weak, the sodium ion, which is neither acidic nor basic, and it's just a spectator. It's not going to have any bearing on the actual reaction. And then we have the acetate ion, which is the conjugate base of acetic acid. So we've identified our species that are going to participate in this. The second step is to identify the equilibrium reaction where we're going to get the hydrogen ions, which is going to control our pH. So this is going to be our reaction. We have acetic acid, our hydrogen ions, and then the acetate ion here. And just kind of as a reminder here from what we were just talking about, the sodium is not going to have any bearing on this because it is not acidic, not basic, so it won't have any bearing on the pH. Okay, so we have our equilibrium reaction, so that's our second step. And then we're going to look at our ICE table here and get our initial change in equilibrium amounts of the species that are involved in this equilibrium reaction. So when we go back and look at the original equation, we have 0.30 moles of the acetic acid, and that is in 1 liter of solution. So our molarity is 0.30. So remember that molarity is moles per liter. So since we just have 1 liter of solution, we just say 0.30 divided by 1, that gives us our molarity. But pay attention to that in case you are given a different amount besides 1 liter. You may have to divide or multiply a little bit differently here, and your initial molarity may not match what is here because of the amount of solution. So that's just something to watch out for. And we know that our initial concentrations of our products are going to be 0. And like our other ice tables that we've looked at, we know that our change is going to be by some amount. The hydrogen ion and the acetate ion are going to increase by that amount, while the acetic acid decreases by that amount. So then at equilibrium, we have our amounts here. Now this is a little different than what we've seen in some of the ice tables that we've done. In that a lot of times we just have an X right here in this last spot in our ice table. But this time you'll notice that we have 0.30 plus X. The equilibrium concentration of this acetate ion is the initial concentration that is due to the sodium acetate plus the change in concentration that we're going to get as the acetic acid ionizes. This is where that common ion effect comes into play. So when you have a problem that involves common ion, be very careful when filling out your ice table and don't just automatically put X in this spot right here, okay? Because when the sodium acetate dissociates, it releases the acetate ions into solution, and we're going to get acetate ions in solution due to the dissolution of the acetic acid as well. So we have the opposites here, 0.30 minus X, 0.30 plus X, because our acetate ions are going to increase on the product side by the amount that they are decreasing on the reactant side. So we've completed the first 3 steps of this, and our last step to be able to solve this is to use our equilibrium constant expression and solve for pH. So here is our equilibrium constant expression. Remember that the products go on top, the reactant on bottom, and Ka is a constant. We can find that in the book in Appendix D or Table 16.2. Then we sub in what we calculated from the table. So X times the quantity 0.30 plus X divided by the quantity 0.30 minus X, and we set that equal to our Ka, which is 1.8 times 10 to the negative 5. Now, since Ka is so small, we assume that X is small comparatively, so we can ignore our X. This goes back to what we were looking at in the last chapter. We can make that assumption that because Ka is very small, X will also be very small and not have a bearing on our overall calculation. So then our expression looks like this. Well, we can essentially cancel out the 0.30 because they're the same on top and bottom, and we're left with X being 1.8 times 10 to the negative 5. And remember what we're solving for here. So X, if we look back up at our table, X is our hydrogen ion concentration, right? And so now we can take the negative log of that to get our pH. So the pH of the solution when we mix acetic acid, which is a weak acid, weak electrolyte, with sodium acetate, a strong electrolyte, is 4.74. So this is due to the common ion effect because both of our initial solutes had the acetate ion. So keep in mind, look for that common ion. All right. See if you have a common ion involved. If so, you're going to have to determine what equilibrium expression we're going to use based on strong electrolyte, weak electrolyte. If there's an ion that's not going to participate, like in this case, the sodium ion, and then just pay attention to your equilibrium for the common ion, in this case, acetate. All right, so that was exercise 17.1. Now we're going to do another problem involving the common ion effect. This time we're not going to solve for pH. We are going to look at concentrations and pH. So not just pH, we're going to look at concentration and pH. So this question says calculate the fluoride ion concentration and pH of a solution that is 0.20 molar in HF and 0.10 molar in HCl. So we've got to figure out what is the fluoride ion concentration and the pH in this solution. So we're going to follow the same steps we did last time. We have to figure out kind of the identity of these solutes. So HF is a weak acid. HCl is a strong acid. And in this case, our common ion is going to be the hydrogen ion. So because HF is a weak acid and HCl is a strong acid, we're going to have three major species involved: HF, the hydrogen ion, and the chloride ion. You think, well, but what about fluoride? Well, remember, HF being a weak acid, it does not completely dissociate. But the hydrochloric acid, being a strong acid, completely dissociates. So we'll have HF, the hydrogen ion, and the chloride ion. The chloride ion is the conjugate base of that strong acid, hydrochloric acid. So it is a spectator ion in anything dealing with acid-base chemistry. So the problem asks for the concentration of the fluoride ion, which is formed from the little bit of ionization that does happen in HF. So since the chloride ion is not important, we don't focus on that reaction, and instead we look at the dissociation equilibrium reaction for hydrofluoric acid. So this is our important equilibrium here. The common ion in this problem is our hydrogen ion. So let's tabulate our ICE table. So for the initial concentration from the problem, we're told that it is 0.20 molar. So there's 0.20 molar. And hydrogen ion concentration is going to be 0.10 molar. And because it told us that. Now, normally you think, well, it's a product, it has 0. But remember that we already have some hydrogen ions that are formed from the dissolution of the hydrochloric acid. So we have to take into account the 0.10 molar of the hydrogen ion there. And then the fluoride is going to be 0. And then our change for each one, going to change by some number. And so now let's set up our expressions. So again, something to pay attention to when you're looking at these equilibrium concentrations here, that we have to be careful when we are putting these in, because they're not just automatically going to be X. Okay, so we have our ice table completed. Now it's time to set up our equilibrium expression. And this is what we have. We have looked at our Appendix D, found the Ka for this reaction, which is 6.8 times 10 to the negative 4. Because that is a small number, we can assume that X then is going to be small, so we don't have to worry about it here or here. And this will be our expression that we're going to solve for. And when we solve for X, this is what we solve for. Okay. Now, X, in this case, when we look up here at our ice table and we see X, we see it this time for the fluoride ion, and that is what we were trying to solve for. So here is the concentration of the fluoride ion that they ask us to solve for. Now, the fluoride ion concentration is substantially smaller than it would be if we had a 0.20 molar solution of HF without the added HCl. So the common ion here, that hydrogen ion, is going to suppress the ionization of HF. The concentration of the hydrogen ion, when we look at that, again, assuming because X is such a small amount, that the hydrogen ion is going to retain that 0.10 molar, and when we solve for pH, we'll have a pH of 1.0. And your book makes a little note here, and it says, for all practical purposes, the hydrogen ion concentration is due entirely to the HCl. The HF makes a negligible contribution by comparison. So basically what happens in this solution is, when we put this into solution, the hydrochloric acid is going to immediately and completely dissociate into the hydrogen ions and the chloride ions. Well, since we're talking about an equilibrium expression here, we already have a lot of hydrogen ions in the solution coming from the hydrochloric acid. So in effect, it suppresses this reaction, because we already have a bunch of hydrogen ions from the HCl. And remember, this is an equilibrium expression. So if we already have a lot of hydrogen ions, we're not going to see a lot of this forward reaction, because we don't need any more hydrogen ions. We already have them from the HCl. Okay, let's move on now to sample exercise 17.3, which gets us into our look at buffers. So remember, a buffer is when we have a solution that contains high concentrations of a weak conjugate acid-base pair, and so it's able to resist drastic changes in pH. We demonstrated this with the lab that we did last week, where we saw that in our buffered solution, we didn't have a wide swing in pH like we did in just the regular solution. So what we're looking at in this question is to calculate the pH of a particular buffer. So we have a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate. And we need to know what is the pH of that buffer. And they tell us our Ka for lactic acid. So we have lactic acid and sodium lactate, a very similar circumstance with acetic acid and sodium acetate. We're just using a little bit different one here. So we first have our equilibrium expression, where we have lactic acid that will dissociate into the hydrogen ion and the lactate ion there. So in your book, they give two ways to work this problem. The first method is the method that we used when we looked at sample exercise 17.1, looking at the common ion. But since we are looking at a buffer solution, we have a special equation that we can use called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is pH is equal to pKa plus log of the concentration of the base divided by the acid. And we are going to use this equation because it is a little bit simpler than going through our entire ICE table and looking at the acid dissociation equilibrium. We can use our Henderson-Hasselbalch here. So they tell us that our Ka for lactic acid is, and I made a typo there, that should be 1.4 times 10 to the negative 4. So let me fix that. Now, the pKa, remember, anytime we are looking at P there, it means negative log. So the pKa is the negative log of Ka. And when we calculate the negative log of Ka, we get 3.85. So just as a reminder, pKa means negative log. It's hard to write in cursive with my mouse, but it's the negative log of Ka. And when we take the negative log of Ka, we get 3.85. Then we add that to the log of the concentration of the base divided by the concentration of the acid. So our sodium lactate in this case is going to serve as the base. And of course, the lactic acid is the acid. So we plug in the concentration of the lactic acid and the concentration of the sodium lactate. And when we take the negative log of that fraction, we get negative 0.08. We subtract that from 3.85, and our pH of this buffer is 3.77. This equation makes it a little bit easier to calculate the pH of a buffer instead of going through the entire process that we did when we were, like, for instance, looking at 17.1. However, there are times when using the Henderson-Hasselbalch equation may not give us the most correct answer, and that's what we're going to look at in exercise 17.4. So exercise 17.4 is calculating pH when the Henderson-Hasselbalch equation may not be accurate. So we have a buffer that contains acetic acid and sodium acetate, and they ask us to first use our equation and then to do it the long way, making no assumptions about our quantities, because when we use the Henderson-Hasselbalch equation, we have to make those assumptions, you know, like we did up here. Let me go back up here for a second. You know, we make the assumptions by not using, you know, the minus x and plus x here, because our Ka values are so small. So in this particular instance, they want us to do it both ways, and make no assumptions there. So the first thing we're going to do here is use our equation, and that's what we've done here. Remember, it's pKa plus log of the concentration of the base divided by the acid. We have our concentrations here that we plugged in, and we've got sodium acetate here, the acetic acid here. The Ka value they told us was 1.80 times 10 to the negative 5, and when we take the pKa of that, we get 4.74. And when we do the math, the pH of this solution we get using the Henderson-Hasselbalch equation is 3.74. All right. That's our pH. Now, they wanted us to redo it, making no assumptions. So let's look at that. So we're back to our same equilibrium reaction that we saw in exercise 17.1. And our initial concentration that they told us was 1.00 times 10 to the negative 3. So that's my initial concentration of acetic acid. I don't have, and I put these in the wrong order. Sorry about that. So we don't have any hydrogen ion yet, but we do have the acetate ion due to the dissolution of our sodium acetate. So this is our acetic acid, our initial concentration of that. And then the acetate ion here comes from the dissolution of the sodium acetate. So we already have some of that in solution. And then we put in our change, minus x plus x. And let's write our expressions here. Okay. So here is our ice table. We've got that all figured out. And now let's look at our equation. Remember, products divided by the concentration of the products divided by the concentration of the reactant equals Ka. When we plug in our values here, this is what we have, and we're making no assumptions, so we're going to end up having to use the quadratic equation. So we plug in our values, okay, and do our math here and cross multiply, and we end up with this equation in the quadratic form. Okay, because remember, we have to rearrange and we have to set our equation equal to 0 in order to use the quadratic formula. We've used the quadratic formula in some of our problems before. It is negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's what we've got set up here. And we're going to just work that down. And when we get it all solved, here is going to be our hydrogen ion concentration. Now remember, when you are doing the quadratic formula, you have that plus and minus. One of your answers is going to make sense, the other one's not. And so in this case, this was the answer that made sense. And when we take our negative log of that to get pH, we get 4.06. Now, with our formula that we just calculated, we calculated 3.74. Now we have 4.06. Why is it different? Well, it's different because in this problem, the acid-base conjugate pair concentrations are only 10 to 100 times as large as K, so we can't assume that X is small. And you say, okay, I don't really understand what that means. What are you doing? So look at our concentrations, our initial concentrations of our acetic acid and our sodium acetate, or our acetate ion here. They're tiny. 1.00 times 10 to the negative 3, 1.00 times 10 to the negative 4. They are very close to the Ka value, within 10 to 100 times of the Ka value. Because our initial concentrations are so small and they themselves are close to the Ka value, we can't make assumptions. X in this case actually does make a difference. Yes, it's a tiny amount, but we're already dealing in tiny amounts with our initial concentration. So you have to be aware of this, when to make assumptions and when not to make assumptions. If your initial concentrations are within 10 to 100 times of your Ka, you can't make assumptions. Okay, just keep that in mind. So let's jump down to sample exercise 17.5. This time we're going to change it up a little bit. We're asked to prepare a buffer. How many moles of ammonium chloride must be added to 2.0 liters of 0.10 molar ammonia to form a buffer whose pH is 9.00? And they tell us here, assume the addition of that ammonium chloride doesn't change the overall volume of the solution. So what we have to look at here is, when we're making a buffer, what are our major species here? So what are the species that are going to be involved? Well, we're going to have ammonia, and of course going to have water here, and then we're going to have the ammonium ions and the hydroxide ions. The chloride ion, remember, that is going to be a spectator, since it is a conjugate base of the strong acid HCl. So the NH4 plus NH3 conjugate acid base pair are going to determine the pH of the buffer. So the Cl here doesn't matter. It's a spectator, just like the sodium was in the other problems that we've looked at. So here is our equilibrium relationship. And when we put this into our base dissociation constant form, this is what we have. Remember that only our aqueous solutions are going to show up in the expression. Water is not going to be a part of the overall Kb expression. When we look up our Kb value in Appendix D, we find it to be 1.8 times 10 to the negative 5. And what we're going to have to do here is a little bit of additional math. We need to figure out the pH, we need to figure out the pOH so that we can determine the hydroxide ion concentration. Remember that pOH is equal to 14 minus the pH. They told us the pH was 9. 14 minus 9 is 5. And then we take the anti-log of that to get our hydroxide ion concentration, which now we know to be equal to 1.0 times 10 to the negative 5. Kb is small, right? 1.8 times 10 to the negative 5. The common ion is present, which is the NH4 plus. The equilibrium concentration of NH3 is going to equal its initial concentration, which is 0.10 molar. So let's rearrange our equilibrium expression to solve for NH4 plus, because remember, what we're trying to figure out is how much of the ammonium chloride do we need to add. And the chloride has no bearing on it. We're looking at just the effect here of the ammonium. So we need to solve for our ammonium concentration. So Kb, which is 1.8 times 10 to the negative 5, multiplied by the ammonia concentration, 0.10, divided by the hydroxide ion concentration. And when we do our math and solve here, we get 0.18 molar. What does that mean? Well, that is for our solution to have a pH of 9.00, which is what they ask us for. So in order to have that pH, the ammonium needs to be in a 0.18 molar concentration. They didn't ask that. They said how many moles must be added. Remember, molar means moles per liter. So we have 0.18 moles per liter. We have a 2-liter solution. So we have to multiply. And so we need to add 0.36 moles of ammonium chloride in order to have a pH of 9.00. Because ammonium, the NH4 plus, and ammonia, NH3, are a conjugate acid-base pair, we could have used our Henderson-Hasselbalch equation to solve this, but we would have had to figure out the pKa and pKb values. So we could have used this one as well. Either one would have gotten us to the correct answer here. Okay, so now we're going to look at another buffer problem here. A buffer is made by adding 0.300 moles of acetic acid and 0.300 moles of sodium acetate to enough water to make 1 liter of solution. And the pH of that buffer is 4.74. This is what you did the other day. You used acetic acid and sodium acetate to make your buffer. You use 25 mils of the acetic acid and 25 mils of your sodium acetate. So this time they're telling us how many moles of each we're adding, and we want to make 1 liter of solution. The pH is 4.74, and they want to know what is the pH of this solution after 5 milliliters of 4.0 molar NaOH solution is added. So you did this the other day in the lab too. Remember, we added drops of hydrochloric acid and sodium hydroxide to the buffered solution, and you measured the pH of that with the pH meter. So this time they're asking us to calculate the pH. So what would happen to the pH after we add sodium hydroxide, which is a strong base, and then to compare that, calculate the pH of the solution made by adding the same amount of the sodium hydroxide to pure water, which you also did because you had water, or I think, no, you didn't use water. You just used the acetic acid solution, and to see what would happen to the pH in a solution that was not buffered. So first things first, we need to figure out our equation here. What is going to be our equilibrium equation? And we need to do a little bit of stoichiometry. And you can look on page 735 in your book, figure 17.3, and I also have this in your notes, and it kind of walks you through the steps that you have to take in order to calculate the pH of these solutions. So first we have to do our stoichiometry calculation to determine how the added hydroxide is going to affect the composition of the buffer, and then we can use the Henderson-Hasselbalch equation or our equilibrium constant expression to determine what. Okay, so let's get into the math of this problem. Here is our equation. And just like before, water does not become a part of our ice table or the overall expression. So let's look at the ice table here. Now, I'm calling this an ice table, but really this is our stoichiometric calculation where we have before the reaction, the change, what's going to be our limiting reactant, and then after the reaction. So not technically an ice table, but an ice table still works. So we have 0.300 moles of acetic acid in 1 liter of solution. So that is going to give us a molarity of 0.300. And then we look at the volumes here. The volumes are going to change because the hydroxide ion right here is going to come from that sodium hydroxide that we're adding. And so our volumes are going to change a little bit. So we have to consider that when we're working these types of problems, when we're doing these stoichiometric calculations. We have to figure out how many moles of reactants and products are going to be produced, and then figure out some concentrations from that. So prior to this neutralization reaction, there are 0.300 moles each of acetic acid and sodium acetate, because that's what the components are for our buffered solution. And therefore, we would also have 0.300 moles of the acetate ion, because right here, sodium acetate, that's going to dissociate, and we'll have sodium ions and the acetate ions. Sodium ions don't have any bearing on this. Remember, they are not acidic or basic, so they don't have any bearing on what's going to happen in our equation here, in our solution. So we don't have to consider that. But we do have the 0.300 moles of the acetate ions. So I'm going to go ahead and plug in right here that we do have 0.300 moles of the acetate ion. The amount of base added, and this is where we have to figure out how much base are we adding. Well, they tell us that we're adding 5 milliliters of 4.0 molar sodium hydroxide solution. So we have to figure out how many moles, because this is what we're looking at here, how many moles then of the sodium hydroxide are we adding? Well, 5 milliliters is equal to 0.005 liters. And it is a 4 molar solution. Therefore, our amount of base added is 0.020 moles. So we're adding 0.020 moles of the hydroxide ion for this equation. Okay. So that's where that comes from. Again, water, we're not, worried about that. Now, neutralizing this amount, neutralizing this particular amount of hydroxide ion is going to require 0.020 moles of acetic acid. So we're going to have to put that in our change here. So we'll have to subtract 0.020. We're going to end up getting rid of all of this hydroxide. So we plug that in, minus 0.020. Okay. And that's going to then add, oops, on this one, the acetate ion. So the amount of acetic acid and the amount of the hydroxide ion both are going to decrease by the amount of the hydroxide, which is 0.020 molar. And the amount of the product, which is the acetate ion, increases by 0.020 moles. So what is our overall, after look like? Well, we're going to have 0.300 minus 0.020 gives us 0.280. We're going to end up with no hydroxide. It's all gone. And we'll end up with 0.320 of the acetate ion. So this is our stoichiometry to determine how much of each one of these we are going to have. Now, when we look at our equilibrium calculation, we're just going to have the same one that we've seen before, where we have acetic acid and that dissociates into hydrogen ions and the acetate ion. And using the quantities of those in our table here, we can use our Henderson-Hasselbalch equation to solve this problem. So the pH is equal to the negative log of our pKa value. And when we calculate that, it is 4.74. And then we've got a little bit something we have to do differently here than what we've had to do before. When we add the 5 milliliters to the 1 liter of solution we already have, we no longer have just 1 liter. We have 1.005 liters. That affects our molarity, which in turn affects our concentration. So we have to then figure out our new molarity by dividing our number of moles here by the new volume. So that's where this comes from. So 0.320 moles divided by 1.005 liters, and then the 0.280 moles divided by 1.005 liters. We take the log of that, add it to our pKa value, and our pH is 4.80. So the initial pH, they told us in the problem, was 4.74. We added the 5 milliliters of the 4.0 molar sodium hydroxide, and that only changed our pH by a tiny amount, 0.06. Now, the second part of this problem asks us to calculate the pH of a solution made by adding the 5 milliliters of sodium hydroxide to 1 liter of pure water. Well, in order to do that, we're going to do a little bit different calculation. So the sodium hydroxide concentration from the sodium hydroxide, 0.02 molar. We already calculated that. We have 1.005 liters. So when we do the calculations and use our sig figs, the molarity, the concentration of our hydrogen ion, is 0.020. POH is the negative log of that, which gives us 1.70. And to calculate the pH, we say 14 minus 1.70 gives us 12.30. So the small amount of hydroxide that we added to the buffer barely changed it. But when we add that same amount to water, which roughly has a pH of 7, then our pH goes all the way up to 12.30. So this calculation just shows us how good buffers are at what they do. So we're going to stop there for this video because our next section gets